Hello and welcome to the Unit 6, Section 1 video on square and cube root function key features and transformations. So, despite the fact that the title to this section is rather long, there's really not much new to learn in this section. So I anticipate this being a fairly quick section for us to go through. So let's start with a square root parent function. A square root function is a function containing a variable under the square root sign. The graph of a square root function is half of a parabola turned on its side. So let's take a look at the graph and see how that comes to be. All right, so just like we've done with the other functions, let's look at some of the coordinates for the square root parent function. And let's start on the bottom. We've got 9 here, and if we were to put 9 into our function, the square root of 9 gives us 3. So our output here would be 3. Now, if we were put in 4, the square root of 4 would be 2. Square root of 1 is 1. Square root of 0 is 0. Then we get to the negative numbers here. Well, we learned previously that if you take the square root of a negative number, we end up with an imaginary number. And since we can't actually graph an imaginary number, we are going to leave these negative numbers out. Okay, so these will not get graphed because we can't physically graph them, because they are not real. So let's graph what we do have. We have 0, 0. We have 1, 1. We have 4, 2. And we have 9, 3. So if we graph those points and then draw our line through our graph, you see that we have something that looks like half of a parabola. If we were extended on the other side of the axis, you would get the other half of your parabola. Now, what we have graphed is a function. If we had the other half of the parabola going below the x-axis, it would not be a function because it would fail the vertical line test. So therefore, in a square root parent function, we only have 1/2 of our parabola, despite the fact that this happens to be an inverse function to x squared. So let's identify some of the features of this function. So if we were to describe the function shape, well, it is half of a parabola turned on its side. Okay, x-intercept is at 0, 0, because we do have a point here, because the square root of 0 is 0. So since we do have a point there, we do have an x-intercept, and that is at 0, 0. Happens to be the location of our y-intercept as well. Now the domain. You're going to look at this and want to say to yourself, well, it's all reals. But that would not quite be the case, because this function does not exist to the left of the y-axis. So the domain is going to be from 0, and we do include 0 because that point is part of the function, 0 to infinity. And then the range is also going to be 0 to infinity when you look from bottom to top. Positive interval, well, it's going to be from 0 to infinity. And this time we do not include the 0 because the value at 0 is 0, and 0 is not positive. There's no negative interval. The increasing interval is from 0 to infinity because it's always increasing, starting at 0. There's no decreasing interval. And then you notice there's one blank for end behavior. That's because there's only one end. And that one end is this one end that has the arrow. So as x goes to infinity, f of x also goes to infinity. And that's the only end that we can do the behavior for because the other end is finite. Well, let's also talk about the cube root parent function, okay, because it's also a radical. Let's take a look at how that looks. A cube root function is a function containing a variable under the cube root sign. The graph of a cube root function is a cubic function turned on its side. So let's go through these x values. The cube root of 27 is 3. The cube root of 8 is 2. The cube root of 1 is 1. The cube root of 0 is 0. The cube root of -1 is -1, because remember, you can have a negative value under a cube root sign, because think about it. What is -1 times -1 times -1? Well, negative and a negative give you a positive, times another negative gives you a negative in the end. So it does work out when you have odd indexed radicals. All right, the cube root of -8 is -2. The cube root of -27 is -3. So let's graph these points. We'll start with 0, 0. We also have 1, 1. Then we have 8, 2. And we can't go to the next one because it goes off the graph. Let's go to the other side. Got -1, -1, -8, -2. And so our graph is going to look something like this. So you notice that this graph looks very much like a cubic function, except a cubic function turned on its side. And there's a reason for that. It's because this is the inverse function of a cubic function. If you go back to Unit 4, the beginning of Unit 4 when we did a cubic function, you had a table that looked just like this, except your y's and x's were in different columns. The values were swapped. So when you swap your x and y values, you end up with a inverse function. So what's the function shape? It's a cubic function that has been turned on its side. All right, how about the x-intercept? Well, it is at 0, 0. The y-intercept, also at 0, 0. The domain is all real numbers. The range is also all real numbers. And our inflection point is at 0, 0. Then we have a positive interval from 0 to infinity. We have a negative interval from -infinity to 0. We're increasing from -infinity to positive infinity, which means we're decreasing nowhere. And this is more traditional in behavior, where we're going to have two statements. The first of which being as x approaches infinity, f of x approaches infinity. As x approaches -infinity, f of x approaches -infinity. So now that we've looked at the two parent functions for square root and cube root, let's talk about transformations. And we only have to talk about transformations for radicals in general because they all behave the same. In fact, they all behave, this one behaves no different than the transformations we've already dealt with. So we're going to kind of go quickly through these. A radical function with a different rate of change, a starting or inflection point other than the origin, and or decreases instead of increases, is simply a transformation of this parent function. So we have this form, and it gives us hk, and the hk here is the location of the starting point for square root functions and the inflection point for cube root functions. So here we have all the rules for the transformations, and it's the same rules that we have dealt with for other functions. If h is positive, we have a translation to the right. If h is negative, we have a translation to the left. Now, that sounds opposite from what you're used to because you're used to it being opposite, right? Well, that's because in the form of the equation, that number for h follows a minus sign. So there's that 2. That 2 is positive, but it looks negative under the square root. Same thing for if your value for h is negative. If I have x minus -2, it's going to look positive because minus a minus gives us x plus 2 under the square root. Now, for a vertical translation up, it's very similar to what you're used to. F of x equals the square root of x plus 4 on the outside. F of x for a translation down will equal square root of x minus 4, that minus 4 being outside of the square root. Now, let's talk about reflections, because so far we have focused a lot on reflections across the x-axis. Now we're going to look at the difference between x-axis and y-axis reflections. And I think this is going to make even more sense here when we look at some examples. But for now, the examples are when a is negative, so therefore when your leading term is negative in front of the square root, you have a reflection across the x-axis. If you have x being negative, that meaning our negatives inside the square root, then you have a reflection across the y-axis. And you can have both, especially with square root functions, and you're going to see what that looks like here shortly. For a vertical stretch, a is greater than 1, so you're going to have something that looks like f of x equals 3 square root of x. And then for vertical compression, that number in the front is going to be between 0 and 1, so something like 1/3 square root of x. So let's do a few examples of transformations. So let's identify the transformations that are occurring here. So for this one, we're translated to the right 4 units and up 3. For B, we have a reflection across the x-axis. And it's important that you tell me which axis is being reflected across. And then we have a vertical stretch of 3. We have also a translation to the left by 1 unit. For C, we have a vertical compression by a factor of 1/2. We also have a reflection across the y-axis. And then that's indicated by that negative in front of the x. And then the -8 on the end tells us that we are translated down 8 units. And then finally in this one, we're reflected across the x-axis because that minus is all the way on the front. We are translated to the left 7. And we are translated up 5, indicated by that 5 on the end. All right, now let's talk about graphing a little bit. So first you need your starting point when you have a square root. So our starting point is hk. So here, h is -2 and k is 3. So we're going to go and plot -2, 3. And since we have no a value, we're not vertically stretched or compressed, so we can go, and we're not reflected at all, so we can go up 1 over 1, up 2 over 4, and up 3 over 9. Now, I'm treating this very much like a parabola because it is half of a parabola turned on its side. So now that we have the function graphed, our positive interval, you're going to be tempted to say all real numbers, but that is not the case here. Even though the whole thing is above the x-axis, the function does not exist prior to x equals -2. So your positive interval is going to start at -2, and we include the -2, and it's going to go to infinity. We're increasing the whole time, but again, we're not increasing for all reals. We're only increasing from -2 to infinity. Likewise, our domain is -2 to infinity. Our range, going from bottom to top, starts at 3 and goes to infinity. And then our end behavior as x approaches infinity, f of x approaches infinity as well. Because on the right side, we're going up. Gradually, but we are going up. Let's check out example B. So our starting point is at 3, -4. So we're going to plot that. 3, -4 goes right here. Now we're reflected, but this indicates reflected across the y-axis. So instead of going in this direction, we are going to be going in this direction, because that is our reflection across y if we have an imaginary y right here along 3. Okay? So now we know generally which direction we're heading. Let's take a look at our stretch. We have a stretch of 2. So remember, we're stretching vertically, which means instead of going up 1, we're going to go up 2, and then we'll go back 1. Instead of going up 2, we're going to go up 4 and back 4. And instead of going up 3, we're going to go up 6 and back 9. So from here, we can graph our function. So there is a rough sketch of the function being graphed. So our positive interval is from negative infinity to 1, okay, because we're positive up until we get to negative 1. Our negative interval is from negative 1 to 3, because remember the function stops at 3. And it is negative at 3, so you can include that negative value at 3. The domain is from negative infinity to 3. And again, we are including the 3. And then the range goes from negative 4 to infinity. And then our end behavior, as x goes to negative infinity, f of x goes to positive infinity. All right, for C, we have a starting point at negative 7, positive 3. So let's plot that. Negative 7, positive 3 is here. We are reflected, this time across the x-axis. So instead of having something that does this, like our parent function, we're going to reflect across our x-axis, which means we're going to have something that looks like this instead. So let's plot in that direction. There's no stretch or compression, so we're going to go down 1 over 1, down 2 over 4, down 3 over 9, and then we're going to draw our function. And so there's our function graphed. Our positive interval goes from negative 7 to 2, and we're positive at negative 7, so we include the negative 7, but not the 2 because the 2 is on the axis. Negative interval from 2 to infinity. We're decreasing the entire way, so from negative 7 to infinity. And our domain is going to be from negative 7 to infinity. This time we include the negative 7. And then our range is from negative infinity to 3. All right, let's take a look at the last example. This one is not a square root, rather it is a cube root. So let's see how we are going to plot this. Very much like what we did before, let's get the inflection point. Instead of a starting point, we actually have an inflection point this time. So it's going to be negative 2, 3. So let's plot that. Negative 2, 3 is right here. We are stretched by 2. So instead of going up 1 over 1, we're going to go up 2 over 1, because 2 is our factor that we're stretched by. Instead of going up 2 over 8, we're going to go up 2 or up 4 over 8. 1, 2, 3, 4, 5, 6, 7, 8. And then we're going to go down 2 and over 1, and then down 2 and over 8, which we don't have enough space for. So we'll draw the graph as we can, just like this. All right, so our increasing interval is all real numbers. It's increasing from negative infinity to positive infinity. Our domain goes from negative infinity to positive infinity. Our range goes from negative infinity to positive infinity. And then we've got our classic end behavior. As x goes to infinity, f of x goes to infinity. as x goes to negative infinity, f of x also goes to negative infinity. All right, let's finish off this section by taking a look at a graph and see if we can write an equation for the given graph. So, first of all, we need to know what h and k and a are, and in these cases, we also need to know what our x is, if it's positive or negative. And that tells us our reflection. So, since this has the general direction of a parent function, we know that it's not reflected, so our x is going to be positive, our a is going to be positive. Now our a value is, we go up 3, we go over 1, and we hit the graph. So instead of going up 1 over 1, you have to go up 3 and over 1 to hit the graph, which means our a is a stretch of 3. Then our h and k is simply our coordinates for our starting point. So we have -9, -7. -9 for h, -7 for k. And we can write the equation for that. That is f of x equals, we lead off with our a value, 3, square root of x plus 9 minus 7 on the outside. All right, let's look at the next example. Our a for this one is going to be negative, and so will our x, because we've reflected not only across the x, but also across the y. So both of these will be negative, and our value for a is going to be 1, because we go over 1, down 1, and we hit the graph. So there's no stretch or compression. hk is our coordinates, 8, 3. And now we can write our equation. F of x equals negative square root of, let me leave enough space for our last term here. F of x equals negative square root of negative x minus 8, and then you have a plus 3 on the outside. Now here's something that's very important. This x minus 8 altogether needs to go in parentheses, because that negative sign has to act on everything that is under the square root. Okay, so make sure you put parentheses on everything with the x minus 8 or x plus whatever, x minus whatever, that's got to go in parentheses if you have a negative in front of it under the square root. You don't need the parentheses if there's no value for h. If you just have the square root of x, you can just put a negative in front of the x and call it good. So that was a couple of square root functions. Let's look at a couple of cube root functions. So let's start with c. Here, we're not so concerned about looking for a reflection across the y-axis. This is more of your traditional a, h, and k will get the job done. So when we look at this, a, if we go up 1 and over 1, we hit the graph. It's increasing, so it's not reflected. So a is 1. H and k is our inflection point. So 4, -5. And then you just plug in your values as you normally would. F of x equals, nothing to write in front, so we go straight to our cube root. Remember to put your index there. Let me make it a little clearer for you. Your index of 3 has to go in the corner, so you are indicating cube root. And then we have x minus 4 minus 5. All right, for this last graph, we have a stretch happening. So we go from our inflection point, we go up 2 and over 1. So we know that the value is 2, and we're also decreasing, which means that our a is negative. And then our hk is -1, +2. That's the coordinates of our inflection point. And so from here, we're just going to write our equation. F of x equals -2, lead with your a value, cube root of x plus 1 plus 2. So again, a lot of this section is just retread of things that you've already done. As we move into the next section, we're going to talk a little bit more about working with these equations, equations that are radical equations. So we're going to talk about how you solve equations with nth roots and rational exponents. That's coming up here in section 2.